Good morning, I'm Riccardo Castellanza from Milan University of Bicocca. Today I will give you a webinar with the title Evaluating the Stability of Landslides and Geostructure with Numerical Analysis. First of all, I want to thank my collaborator, in particular Professor Claudio Di Prisco and Gabriele Frigerio from Politecnico of Milano, Professor Giovanni Costa from my department in Bicocca, and Dr. Matteo Ciantia, Imperial College London, because they helped me in the case study that we did recently, and I will show you today. The content of our presentation are here. First of all, I want to introduce you in what we consider geotechnical modeling. Then I want to define some key point of the strength reduction method that is really very useful for the stability assessment on landslide and geostructure. In fact, in point 3 and 4, I will show you some case studies. And then, just at the end, a quick to the demonstrative case study with GTS NX. Let's start with the geotechnical modeling, point number 1. About the geotechnical modeling, I want to start with the best practical starting point based on my experience. I want just to recall 3 sentences by 3 persons that I was lucky to meet. The first is by Luigi Giussani. He speaks about how we are made. In fact, he says, reason is like an eye, staring at reality, recording its connection and implication, penetrating reality, moving from one thing to another, yet conserving all of them in memory, try to embrace everything. This is what makes us human. What I want to say, the starting point of the geotechnical model is based on our human experience, in the sense that we are really able and we need to collect and to see and to discover all the small aspects of reality. Reality will be, in this case, of course, a real geotechnical engineering problem, and only us have to take into account all the things that then should be put in our model, using an approach that will be, as called by Professor Nova, a rational approach, calculation, that is different from the intuitive perception that was usually used, and in particular before, of the diffusion of this geotechnical modeling, including the finite element code. In fact, the rational calculation allows the definition of the structure's dimension and safety assessment. This is our goal, to enter in deep, to take into account all the detail that we discover looking at the problem. So, the last sentence was by Professor David Muir-Wood, and is relating to the modeling. Modeling forms an implicit part of all engineering design, but many engineering engage in modeling without consciously considering the nature, validity, and consequences of the supporting assumption. It means that many engineers make use of numerical modeling, but may not be stopped to think about the approximation and the assumption that are implicit in the modeling, still less about the nature of the constitutive model that may have been invoked. This is important because from a real problem, as you can see here in the next slide, from a real case study, that is the description of the phenomena, we need now to arrive to a model. Why the model? Because we want to predict the behavior, and then when we perform a nice prediction of a geotechnical engineering problem, including landslide or geostructure, we can now start to think about the job, that is the work, the geotechnical work, to create a bridge, to reinforce a slope, or other things. So what is really very interesting for us is that we need to move from a real case, from reality. So we need to take into account all the many details of a single problem. We need now to select the most important, the key points, the key process of the real case in order to put it in the model. Model means that with respect to our infinity aspect in the real problem, we need to select few aspects, 5, 10, 20, 100, just because the model is an approximation of reality. And then there is the point to have a judgment of the model, to be sure that the model is enough feasible to perform good prediction. This is our key point. And then when the prediction will be enough secure, we can say, or good, we can start to think about the job. This is a job that usually is done by a synergy between the engineering geology world and the geotechnical engineering world. In fact, the engineering geology, in my opinion, have to be, but not only the engineering geology, also the general engineering, they both have to take in mind all these steps. Of course, the engineering geology will be more on the first step, while the general engineering is more on the model step. But anyway, let's see more in detail what I mean. In fact, I mean that thinking on my experience and starting from focusing and observing the physical process of the problem, the following step will be considered. This is based on my experience. Step 1, what are these? This list is the step that, in my opinion, are necessary to perform good geotechnical modeling and good prediction. So step 1 is the most important. Step 1 is the framing and defining the preliminary working hypothesis. What I mean that when anybody of you will be called to study a problem, a landslide or other things, you go there and you get the first impression. You go there with your background, with your tools, continuum, discrete method, I don't know, whatever you have, kind of test. You go there, you see the problem, and you start to think how you can study it, how you can get a good prediction. In fact, then you start to organize what I call in phases, the experimental phases that are really step 2 and 3, where step 2 is the topographic and hydrogeological survey that are necessary to understand the boundary value problem. Definition of a two-dimensional or three-dimensional geometry feature to be included in the model. Why the working hypothesis is so important? Because when you go there for the first time, you just have to decide if you want to perform a 2D or 3D analysis. In fact, for instance, if you are sure that you will need a 3D analysis, you can ask for a laser scan or other instruments to detect a good geometry model. The same for the topographic and hydrogeological survey. When you have the working hypothesis, you have already to ask for money or for people that will do a very good survey that will be useful for you. In fact, in step 3, we need to perform the in situ and the laboratory experimental campaign for the characterization of geomaterial. And this is very important, will be based on the phenomenological model that will be used. In fact, this dot line means that when we are going to ask for an experimental campaign in situ and laboratory, we need already to have in mind the constitutive and the phenomenological model to be used. In fact, as usual occur, that is not good, some person, usually engineering geology, perform the in situ and laboratory test without having in mind the constitutive model and the phenomenological model that the geotechnical engineer will going to use, so that when the engineer are going to start and looking on the report of the in situ, they does on the laboratory experimental campaign, usually they don't find the laboratory data, the experimental data, sorry, that will be useful for the estimation of the parameter and the state variable. So really, step 3 and step 4 are absolutely linked. In fact, in step 4, that is the phase number 2, that is theoretical, and step number 4 is the choice of the constitutive and the phenomenological model to be used, the estimation of parameter and state variable on the basis of the experimental evidences, and including the validation of the chosen theoretical framework. It means that if we have, I don't know, some, for instance, triaxial tests or other things, we can select the proper constitutive model and we try to simulate, we can check if our model is at least suitable to simulate the laboratory test that have been performed. It is not true. If the model is not suitable, we cannot use the model to perform good prediction. This is the point. So the theoretical include also to choose the framework. the theoretical framework, in the sense that if we are going to select, for instance, and we'll see later on, a theoretical approach based on continuum mechanics, we need also to use the full system of partial differential equation that describe the geotechnical problems, so that we can now arrive to phase 3, that is numerical. Why? Because if we have selected a set of partial differential equation that we need to be integrated, the step file is exactly the construction of the FEM model, the execution of numerical analysis in stage of the boundary value problem. That is essentially the integration in an approximate way of our theoretical model. So that then we have the step 6, that is one time, and this is a very hard job, the step 5, to create and perform the numerical analysis, to predict, to have good prediction. Once we have product many numerical analysis, that is many result, there is the key point, step 6, that is the critical assessment of the results. What I mean? I mean that usually, in particular now, 3D constitutive model, including GTS NX, are tools that produce plenty of results. The point is to say if these results are good or not. That is the critical assessment. How we can do it? We can do, and this, using our brain, of course, but mainly comparing them, the numerical result, with the simple analytical and or empirical models. Once that we have performed all this path, that in my experience is very nice, very interesting, and very useful, and we are sure that we are confident, at least, that the results are good, the predictions are good, we can arrive to design and construction of a geotechnical project. For instance, in case of landslide or geostructure, remediation measurements. What I say before is more clearly expressed by picture on this slide. So now, from now in advance, the slide will be full of picture. So don't worry. What I want to say that the phases, as I told you before, 3 phases: the geometrical, geometry and experiments; second, theoretical framework; and third phase is the numerical prediction. The numerical could be expressed in this way. You can see here a building, an historical building, that is the problem, the working hypothesis. Here you can see the 3D model in terms of 3D geometrical model, and here a simplified result of the soil and rock substratum. This is a work performed in Rabat in Morocco with Alpina company using GTS. Why this is important? Because after this setting the geometry and the experimental phase, so the experimental phase, essentially we enter in the theoretical framework. What means that we enter in theoretical framework? It means that we have really a system, as you can see in the Nova book that is cited in the slide before, in soil mechanics by Wiley. In general, we can think that what we have is a really system of partial differential equation, where it is the equilibrium of the solid skeleton, the compatibility equation that link displacement and the strain. The previous one was an equilibrium in terms of effective stress, including the seepage forces. Then, so equilibrium, compatibility, and now constitutive model for soil or rock that link, from an incremental point of view, the effective stress and the strain. And then there are the continuity equation of fluids that bring the two words of the fluid and the solid that usually are in present in geomaterials, so in geotechnical problems, they link together. Because if we have a flux, an incoming flux and outcoming, you can do a balance, and if we have an unbalanced system, we can have volumetric strain. So this is a continuity equation for fluid and solid. Essentially, except from the dynamic part, this system is suitable to solve is the base. Then there are many other systems that are an extension of this, are able to solve the problem that is shown on our left. So to solve this, the point is that we cannot do an analytical integration of this system. So we need now to add boundary condition and the initial condition that are the base for integration, but we need to do we can only perform a simplify that we can call approximate integration using the finite element method. So here we arrive at the finite element discretization that is suitable, is the really only tool from a practical point of view that give us the possibility to do the integration of this system. Of course, there is not only the finite element method, only also other numerical method like finite difference method, but this is the most common, and this one that is the one that is in Geotechnical tunnel system GTS NX. So here now we have the numerical prediction, that is the approximation of our solution of our boundary value problem. Now we can here you can see an example of the displacement of one of the results and in the work that has been done. But this is just to tell you that when we think to the geotechnical model, the main steps are here represented, and in particular, from my experience, the core of the problem is I call the heart of the geotechnical model are the constitutive model of soil and rock. This extremely affect the result and so the prediction. So it is important, very important, to choose properly the constitutive model, how to use it, as you can see later on. Then the body of the geotechnical model, that is what finite element what give us the possibility to solve the problem, is really the finite element method discretization, that means the integration of the problem. Let's see now the strength reduction method. Okay, let's see now the strength reduction method. It is the base in terms of method that we consider for landslide and geostructure stability evaluation. First of all, I want to recall the approaches that usually is used for the slope stability assessment. The first, very common, the limit equilibrium method. It means that the soil mass is divided in slices, and some assumptions are made to satisfy the equilibrium, as we can see later on. In other words, as you can see in this picture, the idea is to find the most likely failure mechanism when many possible failure surfaces will be provided. So there are some assumption and restriction. It's mainly 2D, as you know, Bishop, Spencer and Yambu method, but also some extension to 3D with simple topography could be done. The other method that is more flexible, of course, is the finite element method, that is working really the same way, both in 2D and 3D, and complex geometry could be considered. In this case, the equilibrium is attained by the continuum mechanism, so the previous system of partial differential equation is the one that is really here considered. So no restriction regarding the geometry and besides, no restriction regarding the geometry and heterogeneity should be considered. It means that we can consider any geometry and complex stratification that we want, and we can also include reinforcement. The other advantage is that no arbitrary assumption is required for the shape of the failure surface. In fact, it will be determined by the analysis. Then another positive point is that various elastic plastic soil model, that means different constitutive model, could be considered. And you know that there are different constitutive models that are more suitable for the simulation the mathematical simulation of the different geomaterials. In other words, globally we can say that both the safety factor and the failure behavior could be determined. We can see in fact that we can have a look of the failure mechanism as it is going to be produced. We can see very well this point in the case study that we are going to show later on. Then, in summary, we can think that if we compare the finite element with respect to the limit equilibrium in terms of equilibrium, stress, deformation, failure, and kinematics, we can see that the finite element satisfy the equilibrium satisfied on the continuum, while for the limit equilibrium it is satisfied only for the slices. The stress are computed on the entire continuum, while here they are computed approximately only on certain surface. Deformation are again computed in all the continuum, here are not considered. For the failure condition is checking in all the Gauss point of the all element that consider our boundary value problem, while in this case the failure is allowed only on certain predefined surface, and no check on the yield is considered outside. Again, for the kinematics, the failure surface satisfies the kinematic constraint, while here kinematics are not considered, and the failure mechanism may not be feasible. So, as you can understand, the finite elements are for sure more flexible than the limit equilibrium. Let's go ahead. Let's focus on the finite element approach for the slope stability evaluation. In this case, we can consider in two different ways to evaluate the stability. The first is based on the increase of the applied load. It means that all the material properties are kept constant, while the load, for instance the weight of the superstructure and the groundwater level, are increased. These loads are increased until the loss of stability. It means that we run the analysis, we can find out the failure mechanism and the ultimate load that in this case will be determined, so that the safety factor could be evaluated by the increment that we have introduced in the load in order to arrive to a failure mechanism. The second approach is based on the reduction of the strength characteristic of the soil. It is the so-called CFI reduction method. In this case, the self-weight and the additional load are applied at their nominal value. It means that they are kept constant, while the strength characteristic of the soil are reduced until the loss of stability. It means that we are going to run step-by-step analysis where we are going to introduce a strength reduction factors. As a result, the failure mechanism and the safety factor on the material property are determined. We can ask to ourselves which of the two methods is preferable, is the best. In general, we can consider that the uncertainty is usually larger on material property than on applied loads. So we can conclude that the strength reduction method is in general preferred. Let's, as a consequence, go ahead entering deep of what we consider strength reduction method. In this slide, in order to evaluate in the strength reduction method the factor of safety, we need first of all to consider geometry, and divide it in different infinite element mesh, and then consider the constitutive model, in particular the failure criteria, that as you can see here will be the criteria proposed by Moore-Coulomb. What we are going to do, we can define a sort of safety factor as the ratio between the nominal shear capacity and the reduced shear capacity causing failure, as it expressed in this equation, where tau is the shear strength along the failure surface G, that is, for instance, this surface. So if the slope is stable, we can think that the safety factor is greater than 1. So, which is the idea? The idea is to introduce a strength reduction factor that in principle is the same for cohesion strength and frictional strength, that is the friction angle. So if we consider this strength reduction factor that will be step by step greater than 1, and we consider these two equations, we can evaluate a reduce cohesion and reduce friction in this way. So that, assuming the same strength reduction factor for cohesion and for frictional strength, this could be the safety factor that essentially will be equal of the strength reduction factor. What we are going to do? Let's see. We are going essentially to bring our finite element mesh of our slope in an unstable condition. So the point is, how is or what is instability? When we can speak about failure in a finite element analysis? First of all, we need to focus on the non-convergence of the nonlinear static analysis. In fact, as suggested by Griffith and Lane in 1999, a suitable indicator for instability is the non-convergence. It means that no stress distribution can be found that is simultaneously able to satisfy both the plastic failure criteria and the global equilibrium. The second characteristic is that the slope failure and numerical non-convergence occur simultaneously and are accompanied by a drastic increase in the nodal displacement. So we can check the nodal displacement. If they are increased and we are not able to reach any convergence, this could be an indicator of the unstable condition of our slope. We have also the criteria for the non-convergence in a finite element method that I recall that it is essentially based on the Newton-Raphson approach. It means that the energy, the displacement, and the force norm are monitoring during any step iteration at the single step of the analysis, so that the incremental iterative solution procedure give us the possibility to check the energy criteria, the convergence criteria. If we are unable to get convergence in a maximum number of iterations, for instance of the 50, we can think that there is no convergence. So we are unable to reach any convergence. It means that we are in a stable condition, or that our system is unable to reach a new equilibrium condition. We can also think that the accuracy in the determination of the stability limit is depending on the nonlinear analysis control. It means that the size of the safety factor step and the maximum number of steps affect the speed and if we reach or not the convergence, as well as the maximum number of iterations and the type and value of the target of the convergence. In this flowchart, we can more in detail understand what I tried to explain before. Let's think to start with an initial value of the safety factor. We can now add an increment in the safety factor, that is this, and we can have a higher value in the strength reduction factor, so that we can compute a new cohesion and frictional strength value, as you can see here. It means, in other words, that the more Coulomb criteria in all the Gauss point where we want to force the strength reduction will be reduced. The failure criteria is reduced, so we can plastify, and we can have a not equilibrium condition. So we need to get to get convergence, a Newton-Raphson algorithm will start. If we are able to arrive to a convergence, so if the answer is yes, we can go back here, go here, and put another increase, another increment in the safety factor, and go ahead as I told before. So if now we are in a convergence condition, okay, we go ahead and we increase from 1.1, 1.2, 1.3. If now in 1.4 we are not able to get convergence, we move on the right side, and we using a bisectional method, we reduce the increment of the safety factor to half. So we come back here with the reduced increment safety factor. If we are now able to get convergence, we can go in this way. Go ahead. If we are not convergence, we move in this way. Bisectional method. If we again are not able to get convergence, we move in this way. So when after 3 times of the bisectional method for 50 iterations no convergence is proved, we can think that we need to stop, and so that our incremental procedure will stop, and so we can think that we are arrived to the unstable, to the limit equilibrium condition, that means to the instability, and the safety factor that was computed until this point, that means how much we were able to reduce before instability, reaching the instability condition, how much we were able to reduce the cohesion and frictional strength. This will be the safety factor. What I introduced until now is the so-called standard CFI reduction method. Let's now see how it works, considering these simple benchmark examples. In the example number 1, we can see a very simple geometry, and also some parameter in terms of friction angle and cohesion and the dimension. If here we can see the classical structured mesh, and here the results. If we apply the algorithm that I introduced before, we can see in the contour, for instance, the displacement on the deformed mesh. As we can see here, is very interesting because we can have an idea of the contour of the displacement. The fact that here we have a large part of colored red colored area means that we have a sort of almost not quasi-rigid behavior of this part with respect to the other part. The blue part is not moving. In fact, we are going to see the shear strain, in particular the plastic strain. We can see that the formation of a failure surface is really well reproduced, and the system will arrive to the loss of convergence, that means to the unstable condition, when the weight of this part will produce shearing stress on this surface that will be equal to the maximum limit stress that with the iteration are going to be reduced by the strength reduction factor. And in fact, we can follow step by step the displacement field of one marker point, for instance of this point, and when we are going to approach to the final increment that will become unstable, they will transform to an unstable slope, the displacement is going to increase. If we did the same with the limit equilibrium method, the results are here shown, and if we compare, for instance, different software and also different the limit equilibrium solution, we can see that the numerical finite element solution GTS proposed by GTS NX is more accurate and more precise when quadratic element is considered. So this benchmark tells that the method is suitable to reproduce essentially the same safety factor that is usually computed by using limit equilibrium method. So in simple problem it works well. If now we consider this problem that is a little bit more complex, but anyway very simple, this is another benchmark number 2, proposed by Griffith and Lane, in which a weak stratification is considered, so two different set of parameters, one from the yellow mesh and the other one for this mesh, is provided. Similarly, we can see here the failure at the failure surface that as we can see, there is a main failure surface, but also a second unstable surface here. And in fact, the displacement field that are computed in all the points suggest a little bit more complex unstable instability of the landslide at failure. At failure mean after increasing step by step the strength reduction factor, and then computing when we reach an unstable solution, when we are unable to reach a convergence, to satisfy the convergence criteria, this will be our safety factor. If we compare, as we did before, with the limit equilibrium, we can see again that the best solution is when we consider quadratic element. So this was just in 2D. If now we move without any other comparison to an example that really is taken by the tutorial provided by GTS NX, we can see that the same really approach could be directly used for 3D landslide. We have just to change the geometry. In fact, you can see the model geometry is very simple. The model mesh and the parameter of the bedrock and of the weathered soil, this part on the top. Now, if we adopt the similar standard CFE reduction method, when we lose convergence, that when we arrive to failure, and we can evaluate the safety factor looking at the work tree, that is 119, we can also have this. We need now to check the shear strains that are really the indicator of the failure surfaces. Of course, we are now in a 3D, so we need, for instance, using the slice post-processing, so we can look inside our solid and have a nice idea of the unstable zone, that means of the failure surface. So we can just see that in this case no a priori failure surface was inserted in the model, and this would come out by considering the material property, the mesh, and introducing the CFE reduction algorithm. Okay, what we have did until now, essentially, thinking at the first part of the presentation, we really have already did the full geotechnical modeling path, and in particular we were playing with the earth of the geotechnical model, that is the Constitutive model. In this case, here really the failure criteria, using of course the finite element method. In fact, in other words, what we have seen until now is the standard CFE reduction method. That could be probably more clearly understand looking at this picture, because we start at the local level, so in the single Gauss point of each element of our finite element mesh, that we can consider the global level, our boundary value problem. So in the single local level, we start from an initial failure criteria with a certain cohesion and friction angle that is a part of the constitutive model, and we start to reduce introducing a strength reduction factor for the cohesion and one for the friction angle. So as soon as we increase the strength reduction factor, we are going to shrink the failure criteria in this way. What can occur in one point, for instance, in point A, that is at this failure surface? That if this is the stress image in the sense of the more circle of the stress at the point A, the shrinking of the yield surface that coincides with the failure criteria will arrive to touch the stress level, the stress circle, so that if we force the shrinking, this stress level need to change in order to satisfy the continuity equations. When the failure surface that is coincident with the failure criteria shrink, the stress level, the stress of point A, that is the Morcom circle, could change in this way, for instance. When the failure surface that coincides with the failure criteria shrink, the stress state of point A, for instance, is going to change because it can never be outside the yield surface. This is in the plasticity law. So that, for instance, we can have a variation in the stress level A, while if we consider a point B that is far for the shrinking failure criteria, we never reach plastification because there is this distance. Anyway, these occur in the single Gauss point of the single element during the step and the iteration in which we are going to reduce the strength parameter through the strength reduction factors. Why I want to introduce this slide? Because in the standard one we were thinking that the same strength reduction factor were considered for the cohesion and for the friction angle. But if now we consider a different strength reduction factor, we can start to think to a generalization of the strength reduction method. If this that means, in other words, that we can define a strength reduction factor for the friction angle and one for the cohesion, as defined in these two equations. If these coincide, as in the standard CFI reduction method, we can probably more clearly see in this plot, where there is the cohesion and the friction angle, a sort of strength reduction path. Essentially, we can start from this point for the initial value of the cohesion and for the initial value of the friction angle, and if we are going to reduce adopting the same strength reduction factor, it means that we are pointing we want to arrive to this intersection, that is zero cohesion and zero friction angle. So if step by step we are going to reduce, we check the global equilibrium. If we get convergence, we go ahead increasing the standard reduction factor until we arrive to the red cross, that is the lose of where we lose the convergence. So in this point we stop, we evaluate the final value for the cohesion at failure and the friction at failure. If now we want to generalize this, we can also think that the strength reduction factor for the friction angle will be lower than the strength reduction factor for the cohesion. Why we can think to do this idea? Because, for instance, if we consider bond geomaterial or rock, we can think that weathering of this material, so a more physical strength reduction method, could be considered if we reduce more the strength reduction factor for the cohesion than the strength reduction factor for the friction angle. In this case, we start from this point, but we are not pointing to the 0 point, so that we can think to have a sort of strength reduction path similar to this, in which we are brutally reducing the cohesion, so a strong reduction in the cohesion with respect to a slight reduction of the friction angle, as in this way. And again, we are arriving to a red cross, that is loss of global convergence after many times, according to the algorithm I showed before. So in this case, we can adopt that the global strength reduction factor, is a safety factor, will be equivalent to the bigger strength reduction factor, that is the one related to the cohesion, because it's the dominant strength parameter of this geomaterial. This is sort of generalization in order to have a more physical meaning of this algorithm. On the other hand, we can also think that if the strength reduction factor for the friction will be bigger than the strength reduction factor for the cohesion, our sort of strength reduction path will be similar to this. This is very similar to the one that we can consider in a drastic way for the purely granular soil. In fact, if we have, for instance, a sand, a loose sand or a dense sand, where no cohesion at all is characterizing that geomaterial, we can think that essentially our strength reduction method is just so our strength reduction path is similar to this, where only the friction will be reduced, because cohesion initially and finally is always equal to 0. On the other way, if we want to consider in the same plot not the pure granular soil but the pure cohesive soil, we can think that for instance, a soil where no friction at all is there, our strength reduction path will be similar to this one. Okay, this is just an overview of different possibility with respect to not be always in standard condition, and to try to find some strength reduction method more related to a physical process. But this is not the only thing. We can in fact generalize more the strength reduction method by considering, for instance, other failure criteria. Here you can see the UK-Brown failure logic that could be then also eventually simplified adopting more Coulomb failure logic. But if we adopt for rock, for instance, rock mass in particular, in UK-Brown failure logic, how we can consider here a strength reduction method? It's very simple, because we just need to reduce the parameters that control the size and eventually the shape of the UK-Brown criteria, as you can see here, introducing step by step a strength reduction factor on that parameters, as we did for the cohesion and the friction angle. And similarly, we can have a failure mechanism and a global of our landslide or rock mass property problems in the similar way of the previous one. Another, for instance, possibility to another more generalization, bigger generalization of the strength-reduction method is, for instance, one proposed by Nova related to strain hardening plasticity model, in which we can consider an initial yield surface that is going to shrink, for instance, due to real weathering processes. And here you can find a reference of this model. And if we have a stress point here A that will be reached by the shrinking yield surface, in order to respect consistency, the stress point have to move from A to B. This is something that open also the possibility to reproduce using a sort of strength reduction method, chemomechanical chemomechanical coupling to reproduce weathering on bonded geomaterials. But you can find more detail here. Okay, let's see now, finally, not at all really, let's see now, arrive now to the landslide case study. Here we are to the landslide case study. The aim of this point is to show how the strength reduction method could be used in real problems. First of all, let's start to consider the starting point, that is, include or not the failure surface, in the sense that when we are in a real problem, it's not always sure that we know the failure surface, in the sense that if we are working on a pre-existing landslide, where on this landslide some coring or other investigation permit us to detect the single or multiple failure surface, we can in this case directly put the failure surface in the model. So we are speaking of failure surfaces that are known and prescribed in the model. Differently, if the failure surface is undefined, because we want to check, for instance, a new embankment or other slope, where in the moment of the analysis there are no cracks or failure surface, and we want to prove if the slope is in safe condition or not, we can consider case B, where failure surface is really undefined and will be defined and identified by the analysis. Otherwise, we can have an intermediate condition where the failure surface is partially known, so we can insert some constraint. So let's see some possible application in real case study. Case study number 1, we will have 3 case study. All the case study will be 3D. So let's start step by step to understand how we can work. Okay, here we are in an area where there is a rock mountains with 2 deposits of granular soil on the left and on the right. So first of all, it is necessary to collect the topography, the 3D topography. It could be easily done starting from the ISO elevation polyline, as you can see here. We can open GTS NX, the terrain geometry maker, importing the polylines of the 3D topography, as you can see here, and create a 3D surveys that really match very well the 3D polyline of the topography. Once we have did this job, we can start to create a solid, as you can see here, of our area. So here we can see the rock mountains and the 2 deposits, deposit A on our right and deposit B on our left. Then these deposits, in the specific case, as I told you, were excavated the flank of the mountain and then filled with granular soil. both for deposit A and deposit B. You can see here very well the geometry. So the interface at the ground level of the deposit, of the sand deposit, we can say, and the rock could be detected here and also here. If we go there doing some coring and also some geoelectrical and geophysical measurements, we can detect the stratigraphy, so that we can start to create a 3D nerve surface that is the deep intersurface between the intact rock and the deposit. As you can see here, is obtained from the interpolation of 3D point, that, as I told, coring and geophysical measurement. You can also create another intermediate surface, because the sand deposit could be split in 3 parts. The deepest one is a loose soil, while the medium one is a medium dense soil. So this is the intermediate surface, again obtained from a 3D coring and geophysical measurement. That is some specific point done during the in situ investigation. The same for the shallow surface, that is from the top part of the deposit, where the deposit is slightly bonded, and the medium dense sand. So we have now free interface, free surface. What we can do, as you can see here on the right, deposit A, we can start excavating with the first 3D nerve surface, that was the interface surface between the rock, that is all this part, and the deposit that will fill this area, so that this 3D solid is the deepest one, as I told you. So the loose sand, this is the solid for the medium dense sand, and now this is like a sandwich, the solid related to the upper part, so the slightly bonded geomaterial. If now we cut, we can see if our sandwich were done properly or not, as you can see here. For deposit B, we can do the same job, as you can see here, the deep surface, the intermediate surface, again created from geophysical measurements and the coring and core measurements from borehole. We can see also another detail, that in order to create solid, as I showed before, we need to have a sort of overlapping between two surfaces that could be considered as cutting surface of our solid that we create at the beginning, again as in the previous case. And so here for deposit B, we excavated the first solid, the second and the third. So again the sandwich is like this. Now we are ready, we have created the geometry. Usually is the longest job, because here, as I told at the beginning, we need to put all the information from geometry, from in situ experimental campaign, laboratory campaign, all the issues related mainly to the geometry and the stratification. Now we have created our solid, and we can arrive to create a mesh, so the discretization of our boundary value problem, in the sense that the boundary value problem is now well defined, and this is the full domain that we need to integrate, where we need to integrate our equations. Okay, so let's start for deposit A. We can do the mesh. We can insert in the model the property, the parameters, sorry, and we choose the constitutive model. In this case was the Moore-Coulomb, and we choose in the idea where the goal, now I need to clarify, where to evaluate the safety factor of this area, where the failure surface were known and prescribed, in order to give the possibility to build some houses here. So municipality want to know what about the stability of these deposits. So we can perform first of all some 3D CFI reduction analysis using the standard approach that means that we are going to reduce with the same value of the strain reduction factor, the cohesion if there is there, and the friction angle. And so we can see that we arrived to have a safety factor that was greater than 2.5, and this was an idea of the mechanism of the plastifier area that give us the 3D analysis. We did the same for the deposit B. Here we can see a detail of the mesh, a detail of the 3D analysis that was characterized for a safety factor of 3.1. You can see here the internal failure surface that was defined. In this case, it was a diffuse failure surface, not only at the interface level. And then we decide to be sure that this, you can say, significant, to be sure that this value of the safety factor in 2D that was greater than 2 were correct, we decided to cut the deposit using some cutting planes in order to have some and to perform some 2D analysis. This is what we did, in the sense that we extract the surface from GTS NX. We were able now to move and to prepare an analysis in 2D. So this is the 2D surfaces directly extract from the 3D geometry. This is the 2D quadratic mesh. This is the plastic strain that tell us the failure surface or the failure mechanism that could be created in this stratified material. And we can see that and the unstable part, we can see that the loose the deepest part was really constrained by the geometry of the intact rock mass, so only the superficial part was instabilized. These are the analyses at the end of the standard CFI reduction method, and the safety factor was 1.68, so smaller than 3D. The same we did for the other deposits. Of deposit B, you can see here other section. Globally, we did 8 2D analysis. You can see another one, section E, with the mesh, some detail. You can see also that you can really consider a large mesh for the intact rock that never will plastify. We can see here again the deformed mesh, the plastic strain that, as I stressed already, is what can suggest us the formation of failure surfaces inside the model while here we can see the unstable mass. To conclude the case study 1, we can see that the safety factor for 3D analysis is higher than the safety factor of the 2D analysis. This probably is due to the fact that here we can consider the 3D effect of the excavated rock mountain, while here in the 2D analysis no 3D effect is taken into account. On the other hand, we need also to say that the 3D analysis are characterized by a bigger mesh sites in order to reduce the number of nodes, and also if we consider quadratic element, we can have problem of computational time, while so the accuracy in the 3D is smaller than the accuracy that we can get into the analysis where a finer mesh and quadratic element were considered. Okay, let's go now to the case study number 2. The second case study regards the Vaillant landslide. Vaillant landslide is a very huge landslide that occurred the 9th of October 1963. About 300 million of cubic meter fall down from the mountain top, and 2,000 people were killed. As we can see in this picture, the unstable mass entered in the lake created after the construction of the Bayonne Dam, and due to the high speed of the unstable mass, a very huge water waves overpass the dam, fall down in the valley and kill the people that was living in Longarone. The landslide were activated some years before the failure. In fact, you can see here the cracks that were recognized by Müller and Semenza, so that the unstable mass was mapped and monitored during 3 years before the failure. We can see in this plot that the displacement of the stable mass was extremely related to the water level fluctuation of the lake, and in fact the failure occurred where just after the maximum level of the lake was reached. As you can understand, looking at this plot, the Bayonne landslide is a very complex landslide. In fact, there were 3 years of displacement triggered by water level, and then a very rapid and quick failure. Our goal was just to approach this very complex landslide, exploiting something that we can have from a 3D numerical analysis, a numerical model. We have two aims. The first is just to have an idea of the average material property that was leading to a generalized instability. The second, exploiting the 3D model, so the 3D volume of the unstable mass, to understand or to have an idea of how it can deform when the movement, the significant movement bringing to catastrophic failure starts. Anyway, I stress again that are only preliminary results, and this is just what I'm going to show is just to be considered an academic exercise to show how it is possible to do with 3D finite element analysis using the strength reduction method. The key issue is again to start assuming an initial value of the cohesion and the friction angle of the thin shear zone that you can see better here is this red element in the mesh that was recognized to be the no and prescribed failure shear thin layer. Here this is the unstable mass and this is the stable rock mass. We start step by step reducing the initial arbitrary value of cohesion and friction angle that was considered, and we can see in this image the displacement field and the plastic strain that occur starting from the thin shear zone that occur also in the unstable mass that was modeled considering a nonlinear constitutive model. We can see in the snapshot that step by step the displacement affect the bottom part of the stable mass, and also the plastic strain propagates inside the body of the stable mass. As you can see in the second step, the third stage or step of reduction, and again the third, and the five step. This last step tell us that we are speaking of low value of friction angle and cohesion, and we can have a clear idea of how the displacement field evolve inside unstable mass and how the plastic zone propagates. This is just, as I stress, an example. The landslide is very more complex. It could be some just preliminary results. Okay, let's go now to case study number 3. Let's see now case study number 3. We are speaking of a rock slide of unstable mass that you can see here, that is about 8 million of cubic meter, that until 2012 was affected, started to move with acceleration during the snow melting period, as you can see here. One of the characteristics of this rock slide is that a large monitoring system gives us the possibility to detect very well a spatial distribution of the surface displacement, also in deep, so that for this landslide plenty of monitoring data were available. Many information and all the detail of this land could be found in this paper. Here I want just to show some of the aspects that we already discussed before. In particular, how we can perform a model where the failure surface is partially known, so there is something that is undefined. So it's a sort of academic exercise. Let's see. Again, we start from the 3D topography. So as you can see here, the polyline of the elevation give us the possibility to create a 3D surface, topographic surface of the unstable mass, as you can see here. Then we have produced the solids, and we have just considered only the lateral boundary of the unstable mass. It means that only this part was inserted in the model. That, in other words, the external part is of the rock mass were considered stable, while the internal one is considered interested by the strength reduction method. Here the depth was not defined, so the idea is to play with two different constitutive models with a partially known landslide and to see if the numerical model is able to fit with the spatial distribution of the displacement, at least in terms of spatial distribution more than magnitude, and then if the model is able to catch the real failure surface that was evaluated from in situ study, borehole, and many other things, inclinometers, etc. So we create this finite element mesh. As you can see here, for 200 meter depth, no restriction in the failure surface is assigned to the model. So really we are in this case, that is the failure surface partially no. We did the two steps, and that mean the first is to use a standard CFE reduction method adopting the Moore Coulomb criteria. In this case, the last convergence was was obtained for this parameter, and the unstable mass that was evaluated plotting the plastic strain, as you can see here, was compare to the real failure surface. You can see here that we have a sort of agreement, not so bad, but also not so good. The second constitutive model is the so-called joint rock model, in which some family of joints were directly inserted explicitly in the constitutive model, so that the model can plastify according the in situ family of joints. So the deep direction and the angle direction were considered. The direction and the inclination were considered. We can see here that in this case the predicted failure surface is more close to the real failure surface, so that a more sophisticated constitutive model in which the strength reduction method was imposed by different change material parameter was able to fit better the real failure surface. As a result, we can see that adopting the joint rock model, the final shape of the surface displacement fit enough well, so is in agreement with the monitored spatial distribution of the displacement at the time. After this preliminary analysis of the landslide, it was designed to refine the 3D model. In particular, the idea was also to take into account the evolution of the landslide that required to study more in detail some zones that were more active than others, as you can see here, considering this zone. So the model was refined. You can see here the new mesh, and in this model was also it was decided to include explicitly the failure surfaces. So we are now considering a condition in which the failure surfaces were known and prescribed. The idea so now is to study the stability condition of the single zones. Just to give some example of how we decide to work, we have again considered to use the more Coulomb Ciphy reduction method, but in this case consider a different value for the strength reduction factor for the friction angle and for the cohesion. In particular, it was decided that an higher reduction in the cohesion than in the friction angle is more suitable for simulating the rock weathering. In fact, from also experimental evidence, the initial rock involved in the rock slide progressively is reduced to a soil. For this reason, it is more properly to reduce cohesion in a more relevant way than friction angle. So, according to what we already discussed before, it was decided to consider a strength reduction factor of the cohesion higher than the strength reduction factor of the friction angle, and this is the scenarios of the reduction of cohesion and friction angle that would consider in this simulation that get convergence until this point. To perform this, we use the structure state procedure, including a change material according to this table. We can also appreciate more clearly in this plot where the normalized cohesive and frictional strength are reported. We can see in fact that if we start from a normalized cohesion and friction angle forces, we have a reduction up to 40% of the cohesive strength, while the frictional strength is just reduced to 85%. So this is again to give you an idea that you can use the strength reduction method to force some parameter degradation that are more suitable for what you can observe in the experimental rock weathering. The results that give the model when this kind of strength reduction method is applied are here reported in terms of cumulative displacement as soon as we increase the strength reduction. We can see here more in detail the instabilization of the portion that I was mentioned before, and also how the adjacent portion of the to this zone is involved in the instabilization. In fact, you can also plot a graph like this in which the strength reduction factor, by increasing the strength reduction factor, we can have an idea of the increase of the displacement. This is useful because we can, in this area where more than one zone are involved and interacting between each other, we can have an idea which one are more suitable to be instabilized with respect to the other one. As I told you, this is just an example of what you can do with the generalized strength reduction method. Okay, let's now see what about the geostructure case study. Let's consider this gypsum abandoned mine. This is an interesting case because you can see here that we have a free level of an excavated underground gypsum mine that was abandoned 40 years ago, and on the top of it, in this part, some buildings were constructed. And then, as you can see here, if you enter visiting it, we have now the problem of weathering of gypsum that essentially is induced by the water that flowed some of the level of the mine. You can see here that, in this section, that we are really free level with houses on the top. Level number 1 is not flooded. Level number 2 is partially flooded. It is really directly interacting with the houses, while level 3 is totally flooded. We can see in this map the interaction between building and abandoned mine, that is a pillar. And of course, if some weathering and eventually collapse of pillar occur in this area close to the houses, some problem, of course, can have for the building. So the question is, what about the stability of this system? What about the stability of the pillar? And what occurs if some of the pillar fails in terms of subsidence on the ground surface? These are the two questions that we have to face in this case study. Here you can see more in deep what I presented before in terms of thin section. You can also see two aspects. To start with the geotechnical modeling, a very deep geological study in situ also was conducted. Also through two boreholes, one here also to characterize the fine soil where these houses are resting on, and also this borehole that were crossing all the abandoned system of mine, so that we can extract specimen of rock in different weathering conditions. What I mean? I mean that, as you can see here, performing uniaxial tests on specimens that were retrieved from this borehole. In this area we can think that we have a fresh rock because no water was infiltrating arriving here. This is a massive area of gypsum, and in fact we can the strength was the highest in fact, and so we call this area characterized by fresh rock of gypsum. When the specimen of gypsum were close to the area of the flow of these two levels, where we have full air humidity, humidity in the air, sorry, and partial flood, we can see that the strength is smaller than in this case, so we can call this medium weathered. While if we do some tests on specimens that were totally flooded and so saturated in water, we can speak of the highly weathered gypsum. So this is a picture of the weathering process that occurred in the last 40 years in this mine. We also prepare some specimens in this experimental test, also in situ, of the fresh rock retrieved from this part that we immerse in the water that flowed the mines. Doing some tests after times, that is really after 1 year of time, we can have a strength reduction according to the in situ weathering process. So this is a physical strength reduction in terms of uniaxial strength of gypsum. We did also similar tests in laboratory, reproducing a laboratory weathering with a flux of water or in still water, as you can, and different reduction in the limit load were retrieved, so that other different scenarios of weathering were studied. Was also studied a small scale loaded pillar as in situ, that in this case we apply the same stress of in situ. We put this small pillar in a water flux, and after 10 days we were able to record to reach failure, so that this simple test tell us that in case of significant water flux, we can some pillar can reach failure condition. To conclude the experimental test, we also did, as I told already before, many uniaxial tests, but also Brazilian tests and triaxial tests on the rock, so that we can arrive to this very important plot that is the Uke-Brown failure loci or failure criteria, one for the fresh rock, the other for the medium weathered, and the lower for the highly weathered rock. So that this is, as you can understand, really a strength reduction approach using the Uke-Brown criteria that is really based on phenomenological process, that is the dissolution and the weathering, that is the weathering of gypsum. Then arriving to the second phase, that is the numerical study, we produce a very accurate 3D model in terms of geometry, where all the voids, that is the excavation portion of the gypsum, were considered, and also the houses were in 3D georeferenced with respect to the mine, so that this is a fully coupled model, including also the building location and foundation and the gypsum mine, so that now we can start to have a reply to the question that we set. The first, in particular, to the risk number 1, that is the ground level subsidence in case of collapse. So the point is what occur in case of collapse to the houses that were on the top. The other risk is related to water flooded and was studied with a different approach based on the CFD, is computational fluid dynamics, to have an idea of the exondation in case of collapse, but is not the object of this presentation. Okay, you can see here some detail of the entire model and the different geomaterial that is also fresh fresh, the green one is the fresh gypsum, the soil, the medium weathered gypsum, the highly weathered gypsum. So everything was considered. In order to have an idea of the stability condition of the mines, the stability condition of the pillar, we perform first of all an analysis where that gives us the possibility to evaluate the in situ stress of pillar by pillar. In fact, if we now consider the Aubert and Duval approach, we can have an idea. Here you can already see the stress intensification in the pillar using a slice section of the contour. And here you can have an idea of the map that have been produced according to method 1, that is safety factor maps by Aubert and Duval for each pillar. What is the color? The color represents the safety factor. How we define the safety factor in this case? The safety factor is just defined as the limit stress that was evaluated in lab, as I showed before, taking into account the depth in which we have extracted the gypsum, so after the in situ weathering process, that is divided by the in situ stress evaluated by the 3D FEM model. If the in situ stress is close to the limit load, the safety factor is close to 1. That means we are very close to failure. If in situ stress is smaller, is far from the limit stress, safety factor is higher with respect to the for instance in this case to a value of 10s. We can see that level 1 no critical pillar except one here. Level 2 was more or less in safe condition, while level 3 was in very high risk, in the sense that this line of pillar seems to be very close to fail. These analyses that combine the big 3D model were really useful to have a first idea of the critical area. Was also combined with the second analysis that we call method 2, where here plastic non-linear constitutive model were adopted. That essentially here we produce the strength reduction method experimental based that I showed before. So we insert in the 3D model the reduction of the UK-Brown criteria according to what we have discovered in the experiments. And in fact, we the 6 pillars of the lower level, as you can see here, were extremely affected by plastic strain. So also this different approach that is more sophisticated than the Aubert Duval suggests us that the pillars were really in condition of fail. Okay, this was the first 2 steps of analysis. I can summarize. One is evaluating the map of safety factor, and second to confirm this map and this critical area with the non-linear analysis, including the physical rock weathering that will be studied in the experiments. Then last step is related to the subsidence prediction. What means? Since the 6 pillars that I showed before, that are these pillars here with respect to the houses were the most critical, we decide to take out from the model, that is a sort of collapse, to reproduce in the model brutally the collapse of these 6 pillars. You can see here more or less the portion of the mesh where the 6 pillars are, were here below. 2 of these were already excavated. When they fail, also the upper part fail, and this means that we create a numerical scenario where we simulate the collapse of the 6 most critical pillars, and the roof and the pillar that were on the top, as you can see here, here, and here. This is step by step. So when we arrive to step A, that we take out 2 pillars, we can evaluate with the model what about of plastic strain inside, but in particular what about of subsidence on the ground surface. So this is the subsidence of the ground surface that is due to the excavation, that is the collapse of these two pillars. In the step B, we excavated more pillar, and so we created this big cavity due to the collapse inside the system, and here we have an higher or more intense subsidence basin, as you can see here. In the last step, when we take out the entire more critical pillar, we can have this final subsidence basin. What we can say about this? We can say that if we try to predict the collapse of the entire 6 pillar of the lower level, the subsidence basin is really not affected, it exists, but is really not affected the houses, in particular these buildings, this part, and also this. So what means that on the basis of these results, municipality and people involved in this remediation project decide to just put some monitoring to be sure to know if the process go ahead or not. But they decide not to fill the entire abandoned mine with something to prevent the collapse of the pillar, because if the collapse occur, no damage on the building will be produced. So, as you can see in this last slide related to this case study, this is the 3D subsidence basin, and this is the simplification of the houses that were around. So this is just an example, a practical example of how we can use a sort of strength reduction method, including pillar excavation, of the most pillar excavation, to predict the subsidence of these 3D complex abandoned gypsum mine interacting with buildings. Finally, to conclude this case study, I want to show very quickly another case study in which we have some cliff interacting with building with a large extension, as you can see here. And the goal was to evaluate the critical zone along this cliff in order to think about a remediation measurements project. An accurate TLS and multibathymetry survey was done in order to detect the 3D geometrical mode, that means the cloud points. If a large solid was created on the base of the geometrical model, and then a finite element mesh is here shown, very large model that also were that considered not only the load of the building but also some seismic load. Under this condition, pseudostatic analysis, we study the weathering of calcarenite, and we have, as in the previous case, a shrinking, that is a strength reduction physical based approach of calcarenite. We apply a strength reduction method, and we were able to evaluate the most critical zone, as you can see more or less here. This is very quick. I want just to have an idea that you can apply the method that I showed before, starting from the micro scale, as you can see here, the bonding process, thinking to a shrinking that is equivalent to a strength reduction method, and perform a 3D numerical analysis in order to put in evidence the most critical zones, so that finally this very nice place could be checked with respect to the risk. Then, just to conclude this presentation, I very quickly want to give a very overview of a simple 2D demonstrative case performed in GTS NX. You can see here the surfaces. There is here a an house is with a building with load, and we need to check the stability of this slope with respect to the load of the buildings that should be created here and under also seismic load. So we create the surface, we create the mesh, as you can see here, we create the retaining walls, so to have a proper foundation place for the building. The constraints are imposed, the property of the materials, more Coulomb for the rock mass mainly, and then here you can see the self-weight, that is this arrow. Here the load of the buildings, that is here, the future building, and the seismic load in direction up, in up direction and down. These are the load or the loads that are considered. Okay, here very quickly we can have an idea of the construction stage process that we perform. We have an initial phase, then a clear displacement phase, then we put the load, including the seismic load and the load of the building, and in the first stage we perform a strength reduction method analysis. These are the results after the construction of the building. These are the displacement. You can see here total displacement, and these are the final displacement after the SRM analysis, including seismic load. Is interesting, and I suggest always to check the plastic points, the plastic status, because these are the conditions after the load of the building and the seismic load, and when then we perform the strength reduction method analysis, the CFE reduction in standard way, we have an increase in the plastic point, and you can see here. This means that the slope will going to fail after a reduction, strength reduction analysis that tell us that the safety factor was equal to 2.1, and this is the final plastic straits that really are in the final condition before failure. Thank you very much.